Welcome to my channel, The Chemist Chemistry. I am your facilitator, Dozaman. If today happens to be your first time coming across my video or my channel, please subscribe for me. And if this lesson blesses you, like it for me. And don't forget to tell me your mind in the comment section. If you want to chat with me, below this video lesson is my WhatsApp link. Click on it and we will have a fruitful chat. Alright, in today's video lesson, we will be talking about the electron configuration. The electron configuration. In our recent video lesson, that is quantum numbers, we learned that one of the main things that quantum numbers seeks to achieve is how electrons are distributed within the various orbitals in the shell or the energy levels of an atom. And that is what electron configuration is all about. Electron configuration. Electron configuration describes how electrons are arranged in the various atomic orbitals. We've learned that when we take a given atom, the center is called the nucleus. And around the nucleus, we have shells or energy levels. And within these shells, we do have what is termed as atomic orbitals. And it is inside these atomic orbitals that electrons are located. So in writing an electron configuration, one have to consider certain things first. First thing you have to do is that you have to identify the number of electrons. Why? Because it is these electrons that you are going to distribute or arrange within the various orbitals of that particular atom. So after knowing the number of electrons present, because if the species is an ion, being a cation or an anion, the electrons present will not be the same as the neutral atom of that same species. So always there is a need for you to consider the number of electrons first. Then you write the energy level or the shell number, specifically the principal quantum number you are considering. Then thirdly, you write the orbital in consideration. That is the orbital within that shell or that principal quantum number in question. Then the last thing that you have to do is that to indicate the number of electrons that is within that orbital of that principal quantum number on the left superscript or in the box when you are using the box representation or notation. There are three rules governing electron configuration. In order for someone to correctly or precisely and accurately write electron configuration, there is a need for the person to obey these three principles. Failure to obey any of these can alter your configuration and your answer will be wrong. First principle on my list is the Bohr's principle. The second being the Pauli's exclusion or the exclusive principle. And we have the Hans rule of maximum multiplicity or Hans rule for short. The Bohr's principle is also known as the building up or the construction principle. So let's begin explaining them by talking about Bohr's principle first. Bohr's principle, as I said earlier, is also known as the construction or the building up principle. It states that electrons always occupy orbitals of lower energy before those of higher energy. So when you move from the first shell, the second shell, the third shell, as the principal quantum number is increasing, the energy level also increases. Now, look at this diagram here that the German scientist Bohr used to explain what he was actually communicating to the entire science community. we have angular momentum quantity number here being 0. Here it is 1, 2, 3. And in our previous video lesson, that is the quantum numbers, we learned that when the angular momentum quantity number is 0, we are talking about the s orbital, so represented here with the yellow color. When it is 1, we're talking about the p orbital represented with blue. When it is 2, we're talking about the d orbital represented here purple. And when it's 3, we are talking about the earth represented here in green color. So if you don't understand this principal quantum number, angular momentum quantum number, the 4 type of quantum number, that is the magnetic and the spin quantum number, I would like you to watch my recommended video below this link. This particular video, I have the link below. Watch it and you understand the concept very well. All right, let's proceed. So what Bohr is saying is that the orbital with the least energy is the 1s orbital, then the 2s. So as you move from the 1s downward, from the 1s to 2s, then from the 2s you move to the 2p, from 2p you move to 3s, 3s you follow the arrow, you move to what? The 3p, 3p you come to 4s, 4s you come to 3d, 3d to 4p, 4p to 5x, in that order. Just follow the arrow. So as you follow that order, energy level is increasing. Yes, energy level is increasing. And he's saying that always make sure you fill fully those of lower energy first, fully, before those of higher energy. So meaning always you have to fill the 1s first, then from there you move to the 2s, then you move to the 2p, come back to 3s, move to 3p, then 4s, come back to 3d, 4p, 5x, 4d, 5p, 6x, in that order. Yes, you don't fill all the s and then you come to 2p. No, all the p. No. So follow the arrow, follow the diagram. Yes. So this should always be in your mind as a chemistry student or a science student or a scientist. You should know that the 1s has the lowest energy level, then 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5x, in that order. Yes. If you have any question on this also, let me know it within the comment section. All right, let's proceed to the second, being the Pauli's exclusive or the exclusion principle, which states that each orbital can take a maximum of 2 electrons and their spin must be in opposite direction. So in 1925, Wolfgang Pauli came out with this principle, and all that he was trying to say is that within a given orbital, we pick a given orbital being the 1s, the 2s, or the 2p subshells, or the 3d subshells, or the f subshell. Don't forget, and the quantum numbers, we learned that the p, d, and f orbitals are degenerate orbitals. Very good. So when you pick any orbital, what Pauli is saying is that, or what Wolfgang is saying is that each orbital can take a maximum of 2 electrons and the spin must be in an opposite direction. In other words, as we learn under spin quantum number, we learn that within a given orbital, one electron must spin up and the other must spin down. That is the clockwise and the anti-clockwise direction. Yes. So Wolfgang is saying that each orbital can take a maximum of 2 electrons and their spin must be in the opposite direction. In other words, all that he was trying to say is that no 2 electrons can have the same set of quantum numbers. You see, the 2 electrons will have the same principal quantity number, angular momentum quantity number, magnetic quantity number, but different spin quantum number. Yes, that is what Wolfgang was saying. So no two electron can have the same set of quantum numbers. It's never possible. It is never possible. Take note of that. So let's use this model for further explanation. Don't forget, I've taught earlier that a model give a mental picture, okay, of an idea or a concept. All right. So we have a model here. We have the 1s orbital. So this is an electron. We've learned that from quantum numbers. Spinning up. This one is spinning down. So positive half, negative half. That is clockwise and anti-clockwise respectively. We come here 2s. Okay. So spin up, spin down. So this is a correct configuration. When we come to this side, spin up, spin down, correct. Spin up, spin down, correct. But look at this part. The reason why we are saying that here this is incorrect, because look at this here, all the two electrons are spinning up, meaning clockwise. No, it is never true according to Wolfgang Pauli's exclusive principle. So if you give two electrons the same spin, if they are not spinning in an opposite direction but in the same direction, then it means that they are having the same spin quantum number. It is wrong. Let's take note of that. So here they were all spinning up. That is the clockwise direction, and that is the reason why we say that this configuration is wrong. We come here to this, the electrons in the 2s orbital are all spinning downward. That is in the anti-clockwise direction, negative half, and we are saying that it is incorrect or wrong because they must have an opposite spin. One must spin up and the other must spin down, clockwise and anti-clockwise respectively. That is the reason why we are saying that this is the only correct configuration. This and that are wrong. So take note of that. So we have 4 electrons here, 1, 2, 3, 4, meaning we are talking about the 4th element on the periodic table. So from hydrogen, helium, lithium, and beryllium. So this is beryllium electron configuration. Okay, let's move on to the next. So this is the correct configuration. This and that are incorrect. Why? Because here it is correct in the 1s orbital, but in the 2s, all the electrons are spinning up, which is wrong. Here they are all spinning down, which is wrong. One must spin up like this and the other downward. Okay, the last thing is the Hans rule of maximum multiplicity, or Hans rule for short. Hans rule for short. It states that degenerate orbitals, that is orbitals of same subshell, are first filled singly with electrons of parallel spins before pairing with opposite spin. So all that Hans was saying is that orbitals of same subshells, okay, like the P, the D, the F, they are degenerate. Yes. So let's come here and tackle that. Look at this. We have the nitrogen with atomic number 7, meaning we have 7 electrons in the nitrogen atom. All right, so the first shell, we take a maximum of 2. That is from Pauli's exclusive principle. And 2, you have to fully fill it from Bohr's principle before you move to the second shell or the second orbital, which is the 2s. Then when you get to the 2p and the principal quantum numbers, rather, we learn that the p orbital have dumbbell shape and it is oriented on the xpy axis. Very good. So when it is on the x-axis, we term it as the px, y-axis py, and then on the z-axis, we term it as the pz or the pz, respectively. So now, this and they are degenerate. In other words, they are together. All right. They are orbitals of same subshells. So This is how you fill. You first give the first one only one electron, and it must spin up or maybe down. But take note, if you have to give each of them one each before you begin to pair, or before you start pairing in the opposite direction. So what you can do is that you can, when you reach the degenerate orbital, being the p or the d or the f, make sure you give each orbital one electron first. And after doing that, if there are more electrons, then you begin to pair. But the pairing must be in the opposite direction. So you begin by giving each of the orbitals one electron, and they must all be in the same direction, parallel. So if you start here is spinning up, so all of them should spin up, spin up, spin up. That is clockwise direction. Then when you start the pairing, all the pairing must be spin down, spin down, spin down. As simple as that. Not that you fill the first, you give the first spin up and then spin down before coming to the second. No, that is wrong. Like in this case, so this is incorrect configuration because of what happened here. This electron spinning down here should have come here spinning up as well, like this, to make the configuration correct. So that is why this is correct and this one is incorrect configuration. We will be doing a whiteboard electron configuration in our next video lesson. Yes, so to give a clear, vivid explanation of how you are to tackle questions on how to write electron configuration. Now, here too, we have 2, 2, 2, and then 1, 1. So 1, 2. So making 8. So this is oxygen. So we have here, this is a correct configuration. Why? Because oxygen is having, that's the 8th element on the periodic table with 8 electrons. So after giving each orbital, that is the p orbital specifically, one electron each spinning up, then you have to pair, you start pairing in the opposite direction. So it was 8, no more electrons to add up. So that is why the configuration, the pairing ended on the first of the p, the 2p orbitals specifically. So this configuration is correct and this is wrong. Why? It's incorrect because this orbital is empty. This electron should have been here. Pairing must begin only when all the orbitals has been given a parallel spin, 1 spin each before pairing begins. So that is what Hans also said. So Hans' rule, for short, or Hans' rule of maximum multiplicity, state that degenerate orbitals, that is orbitals of same subshell, are first filled singly with electrons of parallel spin before pairing in the opposite direction, or pairing with opposite spin. This will bring us to the end of today's lesson. Stay tuned for the board representation. I'm going to use the board to explain to you well how the electron configuration, question under the electron configuration are being solved in the next video lesson. This is the chemistry. Jesus is the strongest.